Okay, welcome to video 2 in this lesson on the interaction between the heart and the vasculature and the vascular system. So we spent a lot of time up to this point talking about Frank Starling and the relationship between preload and stroke volume and cardiac output. And as preload goes up, stroke volume goes up. Okay, and the same thing here. This is the same thing at a constant heart rate. As preload goes up, if the heart rate is constant, then the cardiac output is going up. Okay, we call this the ventricular function curve. All right. So now, having taken all that time to describe this and go into it in enormous detail, I want you to imagine that this is the morning after your exam in the vital fluid spot. Okay, and you're getting ready to go home for Christmas, and you know, maybe you've had some fluids the night before, and you wake up in the morning and you're in the state that I like to call mind like mush. Okay, and as you get up and you move around and you recover, and maybe this process started the night before, the knowledge gradually leaks out of your head, like out of the ear, and you gradually lose it. And I want you to imagine that you're in that state, and I want you to forget what I've taught you. I'm going to bring it back, but for right now, remove this from your mind. Okay? Let's start over. All right. Here is our cardiovascular system. Right here. Okay. Heart, arteries, veins, and capillaries. So these are your capillary beds. This is your system. Okay. All right. So if I were to take a red blood cell and start here and just track that blood cell all the way around, through the arteries, down through the capillaries, through the veins, down through the lungs, and then back into the left ventricle, and I were to time it and take the average amount of time that it takes for all that to flow, the average would be about 1 minute. We call this the mean circulation time. Okay? All right. And it's important for you to know in this diagram that what comes out here, the cardiac output, is exactly equal to what goes in here. Okay? And it is exactly equal to what is flowing through the system. If I add up the flow through all these capillaries, it will be exactly equal to the cardiac output. So this is 5 liters per minute. If you add all this up through your entire body, you will get 5 liters per minute, and then the amount returned will be 5 liters per minute. All right? Okay. Now, what is the total peripheral resistance? We just calculated this in the previous video. Okay? This is Ohm's law. 90% of life is shown up. 90% of the rest is Ohm's law. Pressure in the arteries minus pressure in the central venous compartment, 102 minus 100, that gives me 100. Cardiac output is 5. Total peripheral resistance is 20. Okay. Now, here's what I want you to do. I want you to stop the heart. Okay. So, at the instant that I stop the heart, at the very instant, no time is taking place, it just stops instantaneously. And at that instant, what is the flow through the system? Okay? Now, the tendency of a lot of people to say, well, it's zero. It's not zero. Not at the instant you stop the heart. At the instant you stop the heart, the pressure here is still 102. The pressure here is still 2. And blood's going to continue to flow from here to here. Okay? It's going to take time for that blood flow to stop. So what happens is flow continues, and you get an increase in venous volume as blood flows from the arteries to the veins, and you get a decrease in the venous return because blood flows to the ventricle, but it's not pumped out, so it just stops. Okay. All right? So our cardiac output is, of course, 0 here. It just drops instantaneously, but it takes a little while for this to happen and come to a new volume because I've still got pressure gradients at the end when I stop this. Okay? So, let's do it again. Here's our system. We stop the heart. Okay? Now, flow continues. Blood leaves the arterial compartment. It enters the venous compartment. Okay? It enters the central venous compartment. All right? And what happens is, volume goes up here, volume goes down here. So what happens to pressure? Well, if the volume's going down here, then the pressure must be falling. And the pressure on the arterial side falls. If the volume is going up here, then the pressure must be rising, right? Okay. So, venous pressure rises, arterial pressure falls when I stop the heart. When will flow stop? It will stop when those pressures become equal. When the venous pressure rises and the arterial pressure falls until they're the same. Okay? When they're the same, blood flow stops. Okay. All right, and at that point, blood flow through the system is zero, blood flow through the heart is zero, and we're at steady state again. It's not a very good steady state because there's no blood flowing, but that everything comes to rest at that point. All right. So, at what pressure do you think that happens? Well, the tendency is to think that it's halfway between the two. So if I started at 2 here, and I started at 102 here, if I go halfway in between, which would be 52, that would be the tendency. That's not actually true. The reason it's not true is because the veins, the walls of the veins, are way more compliant than the arteries. So for the purposes of this lesson, I'm going to say they're 19 times more compliant. So that means that as blood flows here, for every 19 millimeters I fall here, I only go up 1 millimeter here because these walls are stiff and these are really compliant. So these can receive that same volume and the pressure won't go up as much. Okay? And so that's what I just said. And if you solve this mathematically, which I will not ask you to do. There was a time when I asked students to do this, and then I thought, what are you doing? This is nonsense. Don't do that anymore. So I don't ask you to do this on exams anymore. But if you solve it mathematically, you get the two are equal when the pressure comes to 7 millimeters of mercury. So that you'll go up 5 here, and you'll go down 95 here. Okay, and you'll end up at 7 on either end. All right. We call this the mean circulatory pressure. So if you take somebody who just this instant died and the blood stops flowing and you measure the pressure in their circulation, that'll be the pressure. Okay? All right. So, we get changes in venous pressure when our cardiac output falls to 0. So, you can actually graph that on a relationship. And you can ask yourself, what happens to venous pressure when I slow the heart down? Let's say if it's diseased. Okay. The ultimate slowdown is to stop it. That means you've gone from, that means you've gone from 5 to 0 instantaneously. We don't have to do that. But let's see if we can construct this relationship between central venous pressure and cardiac output. Okay. So first, let's take our normal steady state. Cardiac output is 5, mean arterial pressure 102, central venous pressure is 2. So our CVP is 2, cardiac output is 5. We can put a green point here. That's one point on our relationship. Now we can also put a point for 0, right? I stop the heart, flow continues, blood continues to flow from the artery to the veins. And as that happens, arterial pressure falls, venous pressure rises, and we eventually come to a pressure of 7. And we can put a point here, 0 and 7. Okay? We got 2 points in our relationship. Now, let's start that heart back up. And let's make the cardiac output 1. Okay? So, where will the central venous pressure be? Well, we're starting at 7 on both sides, right? We increase the cardiac output. We say it's 1. Okay. So now, my cardiac output is 1. All right? volume is removed from the venous compartment, and it is added to the arterial compartment. Okay? And as that happens, arterial pressure rises, venous pressure drops, and we start to get flow through the system again. So now we go, okay, what's the delta P going to be when we come to steady state again, when our cardiac output of 1 is equal to our systemic flow of 1? Okay? Well, we go to our old friend Ohm's law. Delta P equals Q times R. So that means, what's the resistance of the system? 102 minus 2 divided by 5 gives you 20. So that was the resistance before I stopped the heart. We're going to assume that doesn't change, and we're going to set our cardiac output to 1. Delta P is equal to cardiac output times total peripheral resistance. It's equal to 20. So when the delta P across the system is 20, the flow through the system will equal the flow through the heart, which means 1 liter per minute in this case. And so, what's the venous pressure when that happens? Well, when we're removing volume here, we're gaining volume here. We know that as we gain volume, for every 19 millimeters of mercury we go up on this side, we're going to drop 1 millimeter of mercury here because the walls of the veins are more compliant than the walls of the arteries. Okay? So we're going to rise here, we're going to fall here until we get a delta P of 20. So that means if my arterial pressure goes up 19 and I fall by 1 here, that's going to give me a delta P of 20. Okay? All right. And so my delta P will be 20 when my venous pressure is fallen by 1 millimeter of mercury, which means that my CVP will be 6 when that happens. I lost a millimeter of mercury on the central venous pressure. I gained 19 in arterial pressure. You've got your delta P of 20, and we've got our new CVP. Okay. And in fact, you can see already this is developing into a linear relationship, and that is exactly what it is. It is a linear relationship between the two. All right? So, one thing I want to emphasize, having walked you through that, is that this is only a part of control of the cardiorespiratory system. The cardiorespiratory system is really, really complicated, so we still have to teach components one at a time, okay? And this component, you should recognize this relationship holds quantitatively only when there are no reflexes, which means no change in total peripheral resistance, okay? And you should recognize that this is not quantitative. So if I'm on the table and they're wheeling me in and I look up and I see you guys in the emergency room and you pull out a graph like this, I'm going to get worried, okay? Because there's a lot more going on than this. But qualitatively, this is always a factor, okay? And I'm going to show you why it's important. It's important to when you consider the symptoms of congestive heart failure. All right, I said that. So, we have our dilated cardiomyopathy patient. Blood pressure is low, heart rate's pretty high, so you know the stroke volume is really low. Okay, and her inotropic state is low. So, if her cardiac output is low, what do you think happens to her central venous pressure? It goes up, right? So if you were to measure the pressure in that patient, you would actually see a higher pressure. And in fact, it's so high that you can see her jugular because it's distended. And so distended jugular is a sign of congestive heart failure. So it relates to something you actually see in a patient. And this is why you see that distended jugular. It's because central venous pressure goes up as cardiac output drops. All right, that's my spiel. That's the end of this video. We'll continue on to the next video when you guys are ready.